We're now going to spend some time looking at carboxylic acids and esters. So here are the first two carboxylic acids in the series, methanoic acid and ethanoic acid, and you'll see they both contain the C double bond O OH functional group, and that's what makes them carboxylic acids. So I'm sure you remember we make carboxylic acids by refluxing a primary alcohol with K2Cr2O7 in acidic conditions, and that will convert the primary alcohol to the carboxylic acid. We make water as well in the process, and it's an oxidation reaction. And we go via the aldehyde for that. So if we start with a primary alcohol and we distill the product off, we will get an aldehyde first of all. But if we keep oxidizing, we will then get to the carboxylic acid. So carboxylic acids are acids, but they are weak acids, which means they only partially dissociate in solution. And the reason why they can partially dissociate in solution is because the minus charge on the oxygen can be spread across those two oxygen atoms. If you compare carboxylic acids with alcohols, which just have the one oxygen, alcohols are not acidic, but because of this ability to spread the negative charge, they can dissociate and release H plus in solution. So we can draw that in a slightly different way with the negative charge spread across those two oxygen atoms. And you'll see this is a very similar way that we draw benzene with the delocalized electrons. In a similar way, the negative charge is delocalized across the two oxygens and the carbon. Short chain carboxylic acids will be soluble in water. That's because they can hydrogen bond with water, but the longer the carbon chain becomes, the more unlikely it is that they will dissolve in water, because the carbon chain is hydrophobic. It will break those hydrogen bonds between water molecules and won't want to get in the way of them. So it will, if you increase the carbon chain too much, they become insoluble in water, but the first few will be soluble in water. Funnily enough, carboxylic acids react like acids, just weak acids. So if you put them with an alkali, they will react with an alkali, and this is ethanoic acid, and that will just give me sodium ethanoate and water. Equally with metals, you will produce the salt, zinc methanoate, and you will produce hydrogen. So that's reacting zinc with methanoic acid. And metal carbonates as well, you will produce the metal salt, water, and carbon dioxide. So don't forget, just because it's an organic molecule, it will still react with like an acid. So esters. Esters you may come across with GCSE. If not, don't panic. Relatively straightforward. You just got to get your head around how to draw them. So you make an ester by reacting a carboxylic acid with an alcohol. You need concentrated sulfuric acid as a catalyst, and you reflux, and that produces an ester and water, and this is in equilibrium. If you start with ethanoic acid and methanol, you produce an ester called methyl ethanoate and water. So let's have a look at those molecules. We've got ethanoic acid, methanol, and methyl ethanoate there. First of all, the water comes from the elimination of the OH from the acid and the H from the alcohol to produce my water. The first part of the name comes from the alcohol, and you just change the anol to il, so that becomes methyl rather than methanol. And the second part of the name comes from the acid, so ethanoic acid becomes ethanoate. So let's just go and have a look again at how that water was eliminated. And you can see the way you draw the ester is you draw the carboxylic acid part first, and as soon as you get to the O of the carboxylic acid, you draw the O of the alcohol and just carry on from there. So that's the key thing as you do the C double bond O of the acid, and then when you draw that bond, that CO is called the ester bond, then it becomes the rest of the alcohol. And that, if you do it that way, you can't go wrong really. So having just created some esters, let's break them up, shall we? And we can break esters up by using hydrolysis. And luckily enough for us, we need to learn two ways. We can react them with dilute HCl, or we can warm them with sodium hydroxide solution. If you use HCl, that's in equilibrium. If you use sodium hydroxide, it's not in equilibrium. And we'll look at the pros and cons of those two methods a little bit later on. So let's have a look and see those two methods. So hydrolysis of esters using HCl, we add water and we break that ester bond there, that carbon-oxygen single bond. When you break that ester bond, you will need to add water across it. So you add back your OH to become the acid and the H to become the alcohol. So the H2O has added like so. So in a similar way, we eliminated them a few minutes ago, we just add them here. If we use sodium hydroxide, we add NaOH. And that's a really important distinction to make. A lot of people get that wrong in the exam, and we just warm that up and it's not in equilibrium. We break the same bond, but rather than producing the acid, we produce the sodium salt of the acid, and we still produce the alcohol. And you can see how the Na and O add to the acid and the H adds to the alcohol. And so rather than producing ethanoic acid, we now produce sodium ethanoate. So in order to make the acid, we need to add some HCl to protonate the acid to get that back. So that involves two-step. So pros and cons. If we use HCl, it's reversible, which reduces yield, but it's good in one way. It's only one step. And key thing is remember to add water in the equation. If we use NaOH, it's not reversible. So the first step, you get a high yield. But you then need to do a further step to produce a carboxylic acid, which then reduces your overall yield. And remember that you put NaOH in the equation.